We will now solve problems using Newton's gravitational law and the concepts of orbital and escape velocities. Let's start with this problem. A 75 kilogram person weighs 735 Newton on the surface of the earth. How far above the surface of the earth would he have to go to lose 10% of his weight? Well, obviously this is related to g, the acceleration due to gravity. Is that right? The value of the acceleration due to gravity at a particular altitude is 10% less than what is on the surface of the earth. We need to find that altitude. A decrease in weight of an object with altitude is caused by the decrease in the value of g, the acceleration due to gravity. G on the surface of the earth is 9.8 meters per second squared and is given by the equation. Can you write down the equation for g on the surface of the earth? We did that in the last class. G equal to gme over re squared, and that is, you know, we can replace the gme by gre squared. Well, if g prime equal to 0.9 g, in other words, we need to find the altitude at which the person will lose 10% of his weight. Where if the person has to lose 10% of his weight, the value of g at that altitude will be 10% less than what we have on the surface of the earth. If g prime is the value of g at that altitude, that g prime will be 0.9 of g on the surface of the earth. Is that right? So g prime, the value of g at an altitude h, which we need to find how far above the surface, will be 90% of the value of g on the surface of the earth. So g prime equal to gme over re plus h all squared. The value of g on the surface of the earth is gme divided by re squared, and the value of g, which we call now g prime, at an altitude h is gme divided by re plus h all squared. And this g prime is 90% of this g. Alright. Let's now replace gme by 9.8 re squared. Is that right? gme is gre squared. So we can replace this gme by 9.8 re squared, and we can use g prime equal to 0.9 g. So there are two things we are going to do here. We will replace this g prime by 0.9 g, and we will replace this gme by the familiar form small g re squared, where small g is 9.8. So 0.9 g equal to gre squared over re plus h all squared. Well, you need now only know the radius of the earth. What is the radius of the earth? You know that value, you need to know it. Well, let's solve here. G from either side will cancel. Divide both sides by g. And then cross multiply. You have re plus h all squared equal to, take this quantity equal to gre squared divided by 0.9. I hope you followed that step. I first cancel the g and then solve for re plus h. Now why? Because we are looking for h. So Re plus H all squared is this GRE squared. No, this G is gone. Re squared over 0.9. And now, therefore, Re plus H is square root of the right side. Square root of Re squared is Re divided by square root of 0.9. Therefore, H equal to Re divided by square root 0.9 minus Re. And now use the value of Re. The radius of the earth is 6.38 times 10 to the 6. Using that value, we get H equal to 3.45 times 10 to the 5 meter. So at this altitude, his weight will be 90% of the weight on the surface of the earth. Okay, I want you to look through these steps, the simplification I did, and make sure you understand those steps. Okay, let's do another problem. If a 1000 kilogram object is projected from the surface of the earth with a velocity of 5 kilometers per second, how high will the object go? Use the standard values of mass of the earth and the radius of the earth. Well, wherever possible, you know, we can replace GME by small g Re squared, thereby eliminate the need for using the mass of the earth. Well, what is this problem asking you to do? You are projecting an object with a velocity of 5 kilometers per second from the surface of the earth. That means when the object is on the surface of the earth, it has a potential energy and a kinetic energy. Tell me, what is the equation for the potential energy of an object on the surface of the earth? It will be negative GREM, negative GMEM over Re. That is the potential energy of an object on the surface of the earth. So this object has that potential energy. It has a kinetic energy because we are giving it this velocity. And now, if it rises to a certain height, we need to find the height. How high will it go? If it rises to a height, when it reaches that height, it will have a potential energy there. How much will that be? Negative GMEM over Re plus H. That will be the potential energy there. And what will be its kinetic energy at that time when it reaches the highest point? When it reaches the highest point, its speed will be 0. So its kinetic energy will be 0. We will find the total energy on the surface of the earth, the total energy at a height h, and use the conservation of energy to solve for h. Alright, let's do that. The mass of the object is 100, now it's a 1000 kilogram. So add another 0 there. Is 1000 kilogram. The velocity that you project that with, the initial velocity of projection is 5000 meters per second. Radius of the earth is 6.38 times 10 to the 6 meter per second. This is a value that we need to use all the time. And GME, remember, wherever we find this quantity GME can be replaced by small g Re squared. Alright, GME is small g Re squared. Okay. What is the total energy of this object on the surface of the earth? Total energy is its potential energy plus its kinetic energy. Now, the potential energy is negative GREM. Is that right? Well, let me refresh your memory on it. The potential energy of an object on the surface of the earth is negative GMEM over Re and that is, replace your GME by what quantity? Negative GRE squared M over RE, and 1 RE on the denominator and 1 RE on the numerator will cancel, leaving us with, oh, it disappeared, leaving us with this: the potential energy on the surface of the earth is negative GREM, and the kinetic energy is 1/2 mv squared, where v we know. Now, let h be the height where the velocity becomes 0. As it rises, it's going to stop at that maximum height. Alright, what is the potential energy at that height h? The potential energy at that height h is negative GMEM over RE plus h. And what will be the kinetic energy at that time? Kinetic energy will be 0. Now, replace your GME by small GRE squared. So the potential energy at a height h is negative GRE squared M over RE plus h. And the kinetic energy at that height equal to 0. Therefore, the total energy will be this quantity. And this total energy must be equal to this total energy on the surface of the earth. The total energy on the surface of the earth is this: negative GREM plus 1/2 mv squared. And that must be equal to the total energy at a height h. That is negative GRE squared m over RE plus h. Now, you need to solve for h from there, and how will you do that? Well, what I will do probably is divide each term by m and maybe multiply each term by 2 so that the 2 from there will go. So that's what I've done. I have multiplied each term by 2 and divided by m. So dividing by m, this m will go, multiplying by 2, negative 2 GRE. Multiplying by 2 will eliminate the 1/2. Dividing by m will eliminate m, leaving us v squared. Alright? So I hope you follow my simplification. What I'm doing is multiply each term by 2 and divide by m. So multiply by 2 and divide by m. Multiply by 2 and divide by m. Now, this is what gives you m and m cancels. This is now negative 2 GRE. And in here, m and m cancels, 2 and 2 cancels, leaving a v squared, equal to what is now here. M and m will cancel. The numerator will be 2 GRE squared, and the denominator is RE plus h. So negative 2 GRE plus v squared equal to negative 2 GRE squared over RE plus h. Remember again, we are looking for h. So what will be your next step? Alright, you can actually put down all these values. Let's put down the values. Negative 2 GRE, negative 2 times 9.8 times, RE is 6.38 times 10 to the 6th, plus v squared, this is the left hand side, equal to the right hand side, 2 GRE squared, 2 times 9.8, this is the radius of the earth, and you need to square it, over RE plus h. You need to now use your calculator to figure it out. Would you like to do that with me? Simplify the left hand side on your calculator and simplify the numerator of the right side. The left side gives me negative 1 times 10 to the 8. Alright, I hope you agree with me. Check it. The numerator on the right side, I get 7.9 times 10 to the 14. Alright, so negative 1 times 10 to the 8 equal to negative 7.98 times 10 to the 14 over Re plus H. The left hand side is negative, the right hand side is negative. You can cancel the negative signs, is that right? That means this Re plus H now equal to this quantity divided by 1 times 10 to the 8. You see how simple it became. And therefore H equal to this quantity can now be simplified and then subtract Re from there. The right hand side, when you simplify this quantity, alright, check it on your calculator. Do you get this as 7.98 times 10 to the 6? Well, if you get it, how do you find H? H equal to 7.98 times 10 to the 6 minus Re. And you know what Re is. So that is, now Re is 6.38 times 10 to the 6. So that is 7.98 times 10 to the 6 minus 6.38 times 10 to the 6. And that is 1.6 times 10 to the 6 meter. That is the height to which the object will go when projected with a velocity of 5 kilometers per second. Alright. It's a nice problem and you must be familiar with doing these kind of problems. Next one. A particle is projected from the surface of the earth with a speed equal to twice the escape speed. When it is very far from the earth, what does that mean? When it's very far from the earth, at infinite distance, what is the characteristic of infinite distance for us? When it is very far from the earth, at infinite distance, the potential energy is 0. That is the characteristics. Then what is its speed? Now, if the object is projected with a velocity equal to the escape velocity, when it reaches at infinite distance, its velocity will be 0. And also its potential energy will be 0. But if you project now the object with twice the escape speed, 2 times the escape speed, when it reaches infinity, it will still have a lot of kinetic energy left. We need to find the speed at that time. Alright, so let's start picking the data. You know that V escape, you remember we obtained an equation for escape velocity. V escape is square root of 2GRE, isn't it? Yes. So we projected our object with a velocity 2 times this. Therefore, velocity of projection, if you cannot read it, watch this. This is V projection, the velocity with which we projected the object. The velocity of projection is 2 times the escape velocity. 2 times square root of 2GRE. And what is the potential energy on the surface of the earth? You must make this equation familiar as accessible to you all the time. The potential energy on the surface of the earth is negative GREM. Alright? What is the kinetic energy on the surface of the earth? Kinetic energy is 1/2 mv squared. And the velocity of projection is 2 times square root of 2GRE. And when you square it, what do you get? Now, squaring 2 will give you 4. And squaring the square root sign will remove the square root sign. So, when you square it, it becomes 4 times 2GRE, right? And 4 times 2GRE will be 8GRE. And there is a 2 on the denominator. The 8 will go with 2, leaving a 4. Well, I have another step there. So that will be 1/2 m times 8 GRE. You know how we got 8. And now that will be equal to 4 mGRE. So the kinetic energy on the surface of the earth is 4 mGRE, and the potential energy is negative GREM. So what is the total energy on the surface of the earth? The total energy is the sum of the potential and kinetic energies. That will be 4 mGRE added to the potential energy minus GMRE, and that will be 3 mGRE. This is the total energy of the object on the surface of the earth. And now we need to find the velocity v when it is very far from the earth. Interpretation: when its potential energy is 0. So if v is the velocity of the object at infinity, its kinetic energy will be 1/2 mv squared, and its potential energy will be 0. The total energy, therefore, at infinity is 1/2 mv squared. And look at how simple this problem is. The total energy on the surface of the earth is 3 mGRE. The total energy at infinity is 1/2 mv squared. Well, you can see all these problems are solved using conservation of energy. The total energy at infinity must be equal to the total energy on the surface of the earth. So according to the conservation of energy, 1/2 mv squared equal to 3 mGRE. And you can see m and m will cancel right away and solve for v. Let's solve for v. We get v squared equal to 6 GRE. Again, multiply by 2 and divide by m will give you this. Therefore, v equal to square root of 6 GRE, and you know g is 9.8, RE is 6.38 times 10 to the 6th. That will give you that velocity is 1.94 times 10 to the 4 meter per second. That means when it reaches infinity, what does infinity mean? Out of the potential well, it has this velocity. That means it will keep going forever with that velocity. Okay, another problem. An object is dropped from rest from a height of 4 times 10 to the 6th meter above the surface of the earth. If there is no air resistance, what is the speed when it strikes the earth? Well, an object is dropped from a very large height and is going to fall to the surface of the earth. We use the same principle. We find the potential energy at this height. Now, what is the equation for the potential energy of an object at a given height h? Potential energy is negative GMEM over RE plus h. That is the potential energy at that height. And it is dropped from that height. What is its kinetic energy? 0. It is dropped. Its initial speed is 0. So its total energy at that height will simply be negative GMEM over RE plus h. Alright? Now it falls onto the surface of the earth. What is the potential energy on the surface of the earth? The potential energy on the surface of the earth is negative GMEM over RE, which is the same as negative small g REM. Is that right? That's the potential energy. And When it falls to the ground, it strikes the earth with a velocity. It has a kinetic energy. We need to find that speed. Its kinetic energy is 1/2 mv squared. The total energy on the surface of the earth must be equal to the total energy at that height, and that is the method we use to solve the problem. The height from where the object is dropped is 5 times 10 to the 7 meter. The radius of the earth is the usual value, and the potential energy of the object at the height h is negative gmem over re plus h. And let's replace this gme. What is gme equal to? Small g re squared. So that will be negative small g re squared m over re plus h. This is the potential energy of the object at the height h. What is its kinetic energy at that height? Is 0. We are dropping it from there. Therefore, total energy at that height is simply this value, negative g re squared m over re plus h. Now, when it reaches the surface of the earth, its potential energy on the surface is negative gmem over re. And replacing this gme by gre squared and simplifying, this becomes negative grem. The potential energy of the object on the surface of the earth is negative grem. And it hits the ground with a speed v, which we need to find. Its kinetic energy on the surface is 1/2 mv squared. So, if you now add the potential energy to kinetic energy on the surface of the earth, that must be equal to the total energy at the height h. The total energy when the object reached the surface of the earth with a velocity v, with a speed v, is its kinetic energy plus its potential energy. 1/2 mv squared plus negative grem, it is this. And now, this quantity, which is the total energy at the height h, must be equal to this quantity, which is the total energy on the surface of the earth. Let's go to the next slide and equate these quantities. Now, I took those two quantities. This is the total energy on the surface when it reaches. This is the total energy at the height h. And we need to solve for this v. Can you do this on your own? Just like we were doing before, multiply by 2 and divide by m. So divide by m and multiply by 2. When you divide by m and multiply by 2, this term will simply be a v squared. What would this be? Divide by m, m will go, multiply by 2. This will be minus 2gre. And what will be the right side? Divide by m, m will go, multiply by 2. It will be minus 2gre squared over re plus h. So, therefore, v squared equal to, now what I did is, I also did one more thing. I moved this term to the right side. So, v squared equal to, I'm going to write this term first, 2gre squared over re plus h, and moved that term to the right side, plus 2gre, so that I have v squared alone on the left side. And now, let's put all these values, that is the challenging part, is that right? Putting them all on your calculator. Well, we know g, that is 2 times 9.8. Now look at the way I write the square of the radius of the earth. 6.38 times 10 to the 6th squared. You must do the same when you use a calculator. All over. Now, on your calculator, you must put this in parentheses, very important. 6.38 times 10 to the 6 plus h is 4 times 10 to the 6 plus 2GRE, the normal value. Okay? Do that on your calculator. If you have trouble with it, let me know. I want to make sure that you can calculate these values on your calculator without any trouble. And that gives me V squared is 4.8 times 10 to the 7 meter per second. Therefore, V is 6,942 meter per second. You can see the method of all such problems is almost the same. We use the conservation of energy. The total energy at the surface of the earth equal to the total energy at other place, wherever that is. Now, we will discuss another important concept related to gravity, and that is Kepler's laws of planetary motion. Much before Newton came out with the gravitational theory, Kepler had done a lot of work on the way planets move around the sun. Now, originally it was the thinking that the planets moved around the sun in circular orbit. But it was Kepler who first came in and said, no, planets don't move around the sun in circular orbit. Their orbits are elliptical. Now, Kepler made 3 important statements about the motion of planets around the Earth. And these are called the 3 laws of planetary motion. Now, this is the first law. Law 1 says planets move in elliptical orbits with the sun at one of the focal points. Now, do you know what an ellipse is and what the focus of an ellipse? Well, let me see if I can take a minute to explain that to you. So, a circle is made up of a set of points that are equidistant from a single point. And that distance we call the radius of the circle, and that single point is called the center of the circle. What is an ellipse? In the case of an ellipse, we have 2 points. And if you can now locate the set of all points such that the sum of the distances from these 2 points are the same. In other words, if you take any number of points on the ellipse and measure the distance R1 and R2 from 2 fixed points, the sum of these distances will always be the same. That is the definition of an ellipse. And these 2 fixed points are called foci. Foci, which is the plural form of focus. So an ellipse has 2 foci. Now, what did the Kepler's first law say? Kepler's first law said a planet moves around the sun in an elliptical path with the sun at one focus. So the sun is sitting at one focus. What that means is, at some times the planet will be closer to the sun, some other times it will be farther away. Well, that is the distinction between an ellipse and a circle. So Kepler's first law, planets move in elliptical orbits with the sun at one of the focal points. Now, here's an illustration of it. Planets move in elliptical orbit with sun at one of its focal point. You can see this ellipse The sun is at the focus. The other focus will be somewhere over here. Alright. Do you notice anything that is significant in the motion of this planet? Do you notice that the planet will move a little faster when it is closer to the sun than when it is farther away? Did you see that? Well, that is a characteristic of the motion of planets along the elliptical orbit. Now, what is the second statement? The second statement is actually will lead us to that conclusion. Which conclusion? The planet moves faster when it is closer to the sun than when it is farther away. It says a line from the sun to the planet sweeps out equal areas in equal intervals of time. What is the meaning of that? If this is the sun and this is the planet, the line joining the planet to the sun will sweep out. As the planet moves, that line sweeps out areas. Now, a very important law, a line from the sun to the planet sweeps out equal areas in equal intervals of time. Now, watch this. As the planet moves around the sun, these shaded areas indicate areas swept out by that line in equal time. Now, you see why the planet has to move faster when it is closer to the sun. In order to trace out the same equal area in the same time when the planet is closer, it has to cover a longer distance. You see that? Because the distance between the planet and the sun is small, it has to cover a longer distance along the ellipse so that you have an equal area like you cover when it is farther away. That means the planet has to move faster when it is closer to the sun than when it is farther away. That is the essence of the second statement. You must be familiar with it. A line from the sun to the planet sweeps out equal areas in equal intervals of time. Okay. Therefore, the planet moves faster when it is closer to the sun than when it is far away. All right. The third law, Kepler's third law is, it is a quantitative law. Look at the statement. The square of the orbital period, you know, orbital period is the time taken by the planet to go around once. The square of the orbital period of the planet is directly proportional to the cube of the average distance of the planet from the sun. Why the average distance? Because the distance of the planet from the sun vary with its position, because the orbit is elliptical. The square of the orbital period is proportional to the cube of the average distance of the planet from the sun. Well, if t is the period of the planet and r is its average distance from the sun, how will you represent this statement? We can say t squared equal to kr cube. Well, look at the little mistake there. The square of the period, the square of the period is proportional to the cube of the average distance. If r is the average distance, it means t squared equal to kr cube. So make that correction there, where k is a constant. Well, let me go back and get rid of it. Okay. Now, consider a planet of mass m sub p, mass of planet, in an orbit around the sun of mass m sub s, at an average distance r from the sun. Alright? the centripetal force to keep the planet in orbit. You remember we talked about it. The centripetal force to keep the planet in orbit is provided by what force? Provided by the gravitational force between the planet and the sun. Alright? If the mass of the planet is m sub p and the mass of the sun is big M sub s, what is the gravitational force between the planet and the sun if the average distance is r? If v is the orbital speed of the planet, then we have mv squared over r, which is the centripetal force. Centripetal force is provided by the gravitational force. This is the gravitational force. Big G ms mp over r squared. The universal gravitational constant times the mass of the sun times the mass of the planet divided by the square of the average distance between the planet and the sun. This is the gravitational force between the planet and the sun. It is this gravitational force that provides the centripetal force mv squared over r for the planet to go in the elliptical orbit. Alright, now you have mp, mass of the planet on either side will cancel. Is that right? This gives the orbital velocity v of the planet. Can you obtain an equation for the orbital velocity v of the planet? V equal to, I'm going to leave it for you to solve this. First of all, 1r on the left will cancel with 1r on the right. mp on the left will cancel with mp on the right. That gives me v squared equal to gms divided by r, or v equal to square root of gms divided by r. The orbital speed of the planet is square root of universal gravitational constant times the mass of the sun divided by the average distance of the planet from the sun. In fact, this equation can be used to find the orbital velocity of any planet if you know the mass of the sun and the average distance of that planet from the sun. Alright? And I have that over here, v equal to square root of gms over r. Okay, if t is the period of the planet and r is its average distance from the sun, we have already used that. Tell me, how do you find the period? Period is the time taken for one complete revolution. In other words, period is the time taken to travel a distance of 2 pi r, which is, well, assuming that the orbit is almost circular. Now, v equal to 2 pi r, the distance traveled divided by the period. Is that right? If 2 pi, we assume that the orbit is almost circular. In that case, the length of the arc for one complete revolution is 2 pi r. And if the period, the time taken to do that is t, then the orbital speed v will be equal to 2 pi r divided by the period. Well, that will be, this 2 pi r divided by t is the orbital speed, and we showed earlier that the orbital speed v equal to square root of gms divided by r. So, equating the two, we got 2 pi r over the period is square root of gms over r. And you can actually get the statement of the third Kepler's law from this equation. Now, that means you square now both sides to get rid of the square root sign. 4 pi squared r squared over t squared equal to gms over r. And can you solve this equation for t squared? Now, what is the statement of the third law? The third law says t squared is directly proportional to the cube of r. T squared is proportional to r cube, or t squared equal to k r cube. Is that right? All right. Can you solve for t squared from here? T squared will be equal to, you can see when you cross multiply, t squared equal to 4 pi squared times r cube divided by gms. And look at the way I wrote it. T squared is 4 pi squared over gms multiplied by r cube. Why did I write it like this? Because 4 pi squared over gms is a constant. G is the universal gravitational constant. Ms is the mass of the sun. So 4 pi squared over gms is a constant. That's okay. Didn't we start by saying that t squared equal to k r cube is the third law of Kepler? So you can see this statement that we got from using directly Newton's law of gravitation. Now, you see, the merit of Kepler's law is that Kepler formulated this law. This is Kepler's law. T squared equal to k r cube. Kepler formulated this law long before Newton came up with his gravitational theory. And look how both these agrees. We got this equation using Newton's gravitational law, and it led us to Kepler's law. That means Kepler's law, which was formulated long before Newton's law of gravitation, both are equally true. Now, what is therefore this k equal to, the constant in Kepler's law? For the solar system, for the planets that move around the sun, this k is 4 pi squared divided by gms. So k equal to 4 pi squared over gms. So if I ask you, what is the value of k for Earth? In other words, when the Earth moves around the sun, the value of k is this. What is the value of this k for Venus? The same thing. What is the value of k for Jupiter? The same thing. For all planets in the solar system, the value of k is the same. On the other hand, if you now want to talk about the motion of a satellite around, say, planet Jupiter, then Kepler's law can be applied there. But it is the satellite that is moving around, and in place of the sun you have Jupiter. So k in such a case will be obtained by replacing the mass of the sun here by mass of Jupiter. Okay? All right. Compute the value of k for the Earth. What is the value of k we just talked about? Is 4 pi squared over gms, g times the mass of the Earth. And that is the value for k for the Earth, k for Venus, k for Jupiter, k for Mars, k for Mercury, all the other planets. The value of k will be the same for all planets in the solar system because it depends only on the mass of the sun. If t is the t for Earth, what is the period of Earth? The period of Earth is 365 days. And r, the mean distance of Earth from the sun, It is actually a constant value which is used very often in astronomy. It is called an astronomical unit. The distance, the mean distance of the Earth from the Sun is 150 million kilometers. That is 1.5 times 10 to the 11 meters. This is the average distance of the Earth from the Sun. So, we know the period of the Earth, we know the average distance of the Earth from the Sun. So, can you calculate K for Earth? So, you can calculate it from this equation right away. We know that the square of the period equal to K times the cube of the average distance of the planet. Is that right? This is the statement of the third law. T squared equal to K R cube. We know the period of the Earth. We know the average distance of the Earth from the Sun. Therefore, K equal to T squared divided by R cube. Alright. K equal to T squared divided by R cube. This is the period, 365 days, converted to hours and seconds, and then square it, divided by R cube. R is 1.5 times 10 to the 11. Alright, calculate that on your calculator and see whether you get this. 3 times 10 to the negative 19 seconds squared per meter, and that is the value of K for the Earth. Once you calculate the value for K for the Earth, you know that this is the same value for Mars and so on. Well, you notice that we calculated K using this equation. K equal to T squared over R cube. But do you remember the quantity K is actually 4 pi squared over GMS. This is the quantity we call the K. Since we calculated the value of K, and since we know the value of the universal gravitational constant, we can now find the mass of the Sun. You see that? Without going anywhere near the Sun, we can now calculate the mass of the Sun from here. I'm going to ask you to do that on your own and let me know. If you can send it to me, I will appreciate that. Calculate a value for the mass of the Sun using the value of K we calculated for Earth. Okay, let's move on. And that is the value of K. Let's do a small problem. Venus has a rotational period of 243 days. What would be the altitude of a SYNCHRON satellite for this planet? Mass of Venus is 0.815 times the mass of the Earth. What is a SYNCHRON satellite? You know that we depend a lot on satellites for our communications. If you have a communication satellite, you want to station that satellite always above a certain point on the surface of the Earth. If there is no synchronization between the rotation of the Earth and the rotation of the satellite, then the position of the satellite will keep on changing as the Earth rotates. That means if you send out a communication satellite, it has to be synchronized. The period of that satellite needs to be synchronized with the period of rotation of the Earth, so that the satellite can be found always above a certain point on the surface of the Earth. Such a satellite is called the SYNCHRON satellite. Now here we are talking about a SYNCHRON satellite for Venus. A SYNCHRON satellite has the same period as the period of rotation of the planet. Is that right? the satellite must have the same period as the period of rotation of the planet. Now the period of the satellite is 243 days. That is the period of Venus' satellite. We are looking for R, the mean distance of the satellite from Venus. Now here, don't confuse here, this is not the solar system. This is Venus and its satellite. You see, earlier we had the planets going around the sun. In that case, we found K is 4 pi divided by G times the mass of Sun. But this time, we have a satellite going round Venus. Therefore, the value of K for this situation is 4 pi squared divided by G times the mass of Venus. So don't confuse here, very important to know that. So we got T squared equal to K times R cube, the square of the period of the satellite, equal to K times the cube of its average distance from the planet. And the satellite is the satellite for Venus. Therefore, you notice here, in place of the mass of the Sun, I use the mass of Venus. And the mass of Venus is given to be 0.815 times the mass of the Earth. And so, we need to find what would be the altitude of the synchronous satellite. We need to find this R. So, if T squared equal to 4 pi squared GM Venus times R cube, therefore R equal to cube root of T squared G mass of Venus divided by 4 pi squared. I'm sure you understand that. R cube equal to T squared times GM Venus divided by 4 pi squared. R equal to cube root of that quantity. Now that will be now T squared G times the mass of Venus is 0.815 times the mass of the Earth divided by 4 pi squared. And I have given you the mass of the Earth some time ago. So that will be T squared, the square of the period of the satellite, 243 days. Convert that to seconds. Times G, 6.7 times 10 to the negative 11. Times 0.815 times the mass of the Earth is 5.98 times 10 to the 24 over 4 pi squared. You can see in this particular part of the course you have a lot of these slightly complicated calculations, and you must feel comfortable using this on your calculator. Okay? And that gives you 1.54 times 10 to the power of 9. If you don't know how to do this on the calculator, well, you can do them piece by piece. In other words, you can do all this quantity, then divide that by 4 pi squared to get you that quantity. And to take the cube root, how do you take the cube root of a quantity on the calculator? Raise it to the power 1/3. That is how you find the cube root. Once you find this number inside the radical sign, raise it to the power 1/3. Okay. Let's do another one. A satellite with a mass of 300 kilograms moves in a circular orbit 5 times 10 to the 7 meter above the Earth's surface. What is the gravitational force on the satellite? What is the speed of the satellite? What is the period of the satellite? Well, let's take the data. The mass of the satellite is 300 kilograms. The height of the satellite is 5 times 10 to the 7 meter. and the radius of the Earth is the usual value, 6.38 times 10 to the 6th meter. First, what is the gravitational force on the satellite? Gravitational force is G-MEM divided by RE plus H all squared. And all you need to do is put in those values. And GME can be replaced by small g RE squared. And now you have G is 9.8, RE squared, 6.38 times 10 to the 6th E squared, times mass is 300 over RE plus H all squared. And again, put that in the calculator and solve it. Is there anybody who wants me to show you how this is done? Well, let me see if there is one person who wants help with it. Alright, I'm going to hold the calculator here and do that for you and see how it goes. It'll be the numerator, you can type in the way you see it. 9.8 multiplied by, in parentheses, 6.38 times 10 to the power of 6, parenthesis closed, and square it, divided by, parenthesis, the parenthesis, 6.38 times 10 to the power 6 times 10 to the power of 6 plus 5 times 10 to the power of 7, parenthesis closed, and square it. It's a very simple calculation, and that will be 0.12549. Is that right? Well, let's check it one more time. Now, you notice that I did not get the right answer. Now, what was the answer I got? The answer I got was 0.12549, but the actual answer is 37.7. Anybody tell me, where did I go wrong? If you watch me do it, I know it. When I was typing the numerator out, I stopped here. I did not multiply by 300. So if you multiply this result 0.12549, which we obtained, by 300, you get 37.7. Okay, well, I made an attempt, and you must be able to put these on your calculator and do your calculations without making a mistake. Well, we did the first part. We found the gravitational force on the satellite. What is the speed of the satellite? How do you find the speed? Now, the gravitational force which we calculated, 37.7 Newton, is a measure of the centripetal force on the satellite, isn't it? Yes, we have used that several times. That means this quantity equal to mv squared over r. So mv squared over re plus h. It is at a height h above the surface, so the distance of the satellite from the center of the Earth is re plus h. mv squared over re plus h is 37.7. Therefore, v equal to, you see, v squared is 37.7 times re plus h divided by m. Therefore, v equal to square root of 37.7 times re plus h divided by m. And all these values we know. So place all those values there. 37.7 times re plus h. H is 5 times 10 to the 7 divided by m. All right, and that gives me 2,662 meter per second is the speed of the satellite while in orbit. What is the period of the satellite? The time taken for one revolution. Well, once you know the orbital speed, you can find the period very easily. If t is the period of the satellite, then we have t equal to 2 pi r divided by v. Well, this r, the distance of the satellite from the center of the earth is re plus h. So the period t equal to 2 pi times re plus h over v. We know all these quantities. V we just calculated. Radius of the earth we know. H we know. Therefore, use all those values, and that gives you the period is 1.33 times 10 to the power of 5 seconds. Well, I think this lesson contained a good number of problems, and you must be familiar with doing all these kinds of problems. All right? That's about 37 hours. And I'm going to stop this one here. I will get back to you with the last lesson later on.